This is the mechanics paper from Pearson Edexcel, June 2019, just regular A-level maths. It's 50 marks, let's do it quickly as possible. So V is this. Of course, if it's given in terms of t like this, that means we're going to differentiate to find A. A is, the acceleration is dv by dt. So let's just differentiate this. You can do it separately, so differentiate the i's for just a 6, differentiate the j's for 3/2 times 5, and then take that down to a half, and you get this apparently. So that's good. And then we're finding that when t is 4, so we just plug in t is 4 into this, and we get this vector here as our acceleration. The position vector is the opposite. The position vector you integrate v to get. So we're going to do the integral of this, which is going to be, we'll raise that to a 2 squared, divide by 2 to get 3t squared, and then do an integral here, and we should get this. Of course, there's a plus c, which is bold because it could be a vector as well. And of course that's just there because we've integrated. Now we've been given an initial condition here though, which is when t is 0, the position is there. So when t is 0, both of these terms go away, so c must just be this thing here. So I'll just say that there as well. And we'll get this as our full position vector. And we're going to find when t is 4. Well, of course we say when t is 4, we just plug in 4s into here. You can do it in a calculator and you'll get this, which ties these up to this. And we'll have our answer for question number 1. So good. So just remember a ladder, maybe. I always have a ladder in my head. Displacement, velocity, acceleration. You go down, you differentiate to go down, so differentiate velocity for acceleration, for instance, and you integrate to go upwards. Good. Question number 2. We have constant acceleration this time, so we're immediately thinking to that. We've been given A, we've been given initial velocity, we've been given final velocity, and we're looking for the time. So that's going to be v equals u plus at, I think, where v is this, u is that, and a is this. Now v isn't actually this, it's saying it's moving in the direction of this, which means it could be any multiple of this vector here. Moving in the direction just means parallel to, so some kind of multiple of this. So I'll just use the letter k here to represent that it could be going in any kind of multiple of this vector, but not specifically that vector itself. So we're going to have k times this is equal to, now this is just u, that's just there, and then a is just from here. Of course we can say minus 1 plus 2t is the top row of this thing here, and 4 minus 3t is the bottom row. And now we can just compare. This thing needs to equal this thing needs to equal this thing, just put the k's into there as well. So we get this and this, and now we're trying to solve for t here, so let's eliminate k. So if we divide this by minus 4 maybe, we'll get this, and then shove it into here, we'll get this, and I think after a bit of maths, which I'm sure you guys can follow, we'll get t is 8. You guys can do that however you want, but t is 8 is the answer you're going to get. When t is 4, p is at point B. Find the distance AB. So we want to know its position when t is 4. Now position is weirdly, for some reason, given as r in this rather than s. I don't really know why they changed to r when you're working in vectors like this. It confuses me. But anyway, r is in the Suvat equation. We're just using r as s here, and this I think will work because we know u, we know a, and we know t is at t4. So we should be able to work out the position vector by just shoving in all of that information into here. So b I think is at this vector here. Now I've said a is 0, 0. I'm just pretending that it's starting at 0, 0. So that way I can say that this is at the position 12 minus 8, and then I can just do Pythagoras from 0, 0 to 12 minus 8, which will just be this, and that will be my distance. Now of course it doesn't really matter, but if a didn't start at 0, 0, say it started at 5, 0, then you would just need to add a 5 to this top bit here to make it 5 further away still. So you just pretend it starts at the origin, and then because it doesn't really matter. And then you just do this in Pythagoras and you'll find the answer. Okay, C is an inclined plane problem. Of course, first we don't do tan inverse of this. We say here's a triangle, 5, 12, opposite over adjacent is 5 twelfths. 5, 12, 13 triangle exists, which means sine of alpha is 5 13ths and cos of alpha is 12 13ths. If you don't do it that way, you're just dead to me. If you type tan inverse, it's just great. Go do geography A-level where you can colour in as well. Why don't you try that kind of thing? Anyway, so we're doing this the proper way. We have 2mg going downwards here. We have 2mg cos theta here, 2mg sine theta there. We have reaction force is the same as this one here. We have a frictional force, which is R, which is the reaction force, times mu. I don't know whether they've told me what mu is. They've told me it's 2/3. Good, I'll fill that in later. So we have that, and then over here we have 3mg just going downwards, because of course that's just the force going downwards. And we also have two tensions, a tension in this rope and a tension in this rope, that are of course the same because it's the same rope. So that's the entire picture. We can replace the causes and the sines with these things here. So I think I'll do that there, so you can work through the fractions if you want to. I've also replaced the mu with the 2/3, it looks like, as well to get this. But that's just replacing all those with the information that I've got on the screen. Here we can set up F equals ma on each of these two blocks separately. So over here, F equals ma says this one, this force going down the plane, plus this force going down the plane, minus this force going up it, T, equals ma, and m is 2m, so that's 2ma. So this one plus this one minus this one equals 2ma. And for this one here, much simpler, it's just 3mg minus t equals 3ma. And the a is the same because they're moving. It's always the same in these questions, isn't it? Because the string we're pretending isn't stretchy or anything like that. So they just move together at the same kind of they correspond to each other in that sense. Anyway, so we can we're trying to find t in terms of m and g. So let's rearrange this for a to get that, and then just shove it into here. And I think does this actually 30 over 39, 78 over 39. 2. Oh, nice, of course. That just becomes a 2. And then we do some maths here, I guess. I don't even know how I've done this. Times through by 2m. And then add this to both sides. Add t to both sides. Divide. Yeah, okay, it's going to work. Eventually, good. So we get this. That's 8 marks. Wow, okay. After b reaches the ground A, continues to move up the plane. So b smacks into the ground, thus destroying or removing any force coming downwards and any tension going upwards. So this tension is going to drop out. A is just going to start moving freely. And the question is actually going to move. And the thing is, if A is sitting a little bit further up the plane here, and there's no force bringing it up any further because B is on the ground, that means it will want to move down the plane, right? Because there will be no force dragging it up. Now, if it wants to move down the plane, that means friction will swap its allegiance and start working up the plane, because it always wants to stop things from doing stuff. But of course, this force will be the same, just the mg cos theta, or sine theta, sorry. And this force this is the maximum frictional force here. But you can see the maximum friction force is bigger than the force going down the plane, right? 10/13 is less than 1, this is bigger than 1. So the frictional force is bigger than this force and will be acting this way. And so the thing won't move, right? Because the frictional force is big enough to stop it from moving when there's nothing else dragging it anywhere at all. Suggest 2 refinements. Just put your normal things. Put some friction in this pulley would be good. Put some mass in this string would also be good. Yeah, I think those are 2 good things to say. There are other things I'm sure you could say, but that's good. Question number 4. So we've got another question about an inclined plane sort of thing here, but it's also going to be about moments as well when you have a question that looks a bit like this. But we're going to set up very similar things. Again, set up the tan triangle, 7 over 24, opposite of adjacent. 7, 24, 25 is a triangle that exists in the world, and then sine alpha is 7 over 25, cos alpha is 24 over 25. Okay, good, so now let's set up some things. So mg for this rod here, now the rod is uniform, I presume, because this is just A-level maths, so it can't be anything else. Good, the rod is uniform. And so, okay, the weight acts halfway along, it's 8 long, so the weight acts 4 meters along it, so roughly here, I guess 1 meter away from this point. That's just mg, and do they tell me m? Yeah, they tell me it's 20, okay. Now, we can do a force perpendicular to the rod itself, which is mg cos theta, obviously. Why have I written alphas here when it's clearly a theta? That must be copying and pasting that hasn't gone very well. Okay, pretend these are thetas, obviously, and yeah, pretend those are thetas. Is that because I used them from the previous question? Yeah, I copied and pasted from the previous question. These should be thetas, not alphas, but whatever, let's just ignore that. So 20g cos theta should be here. In fact, let's just write here alpha equals theta. Just imagine alpha equals theta is written here, and then everything makes sense. Anyway, this is 20g cos alpha, and that's perpendicular to the rod itself. And then we've also got a force coming out perpendicular between this drum and the rod, which we can just call R for resistance force, and we can break that down also into its 2 corresponding forces, horizontal and vertical. Now, just be a bit careful about this. This horizontal one is going to be R sine alpha, or R sine theta, really, it should say. And the reason for that is by alternate angles, theta, theta, theta. So this here is theta, or alpha, because those 2 things are the same thing in my world. And if that's theta, then this here is 90 minus theta, because there's a 90 degrees there. So this is 90 minus theta. But then if you imagine this triangle, that's 90 minus theta, that makes this theta again. So opposite it will be sine. So draw out some more stuff if you need to, and therefore, of course, next to it will be cos. But that's the order you're going to have there. Of course, we can replace all these sine thetas or alphas with the right things, but first as well, we've got a reaction force on the floor with the rod, which we can just call F, and we'll also have a frictional force. Of course, this will want to slip this way, bringing this tip down this way, so the frictional force will be acting this way, and that's just mu F, whatever mu is. I don't know what they tell us yet, or whether that's something we need to work out. But anyway, we can replace all of these things with the things that I've said over here. So let's replace all the important stuff there with those figures, just replacing them with these things there. And now we can set up a bunch of equations based on moments and based on horizontal and vertical movement here. So looking at the, I don't know what first it says explain this. This is the only thing you're allowed to say. So just memorize that answer when you see things like this. It's only 1 mark, so don't worry about it too much. But just memorize to write something like that if it asks you this question. Anyway, part B, the actual maths to do. Find the reaction. So setting up a few things here. I think this is the vertical thing. So F is this vertical, plus 24 over 25R is this vertical, equals 20G is this vertical there. So vertical plus vertical equals vertical there. So that's that statement. We can also do the same with horizontals. So mu F equals mu R. Sorry, equals 7/25 R. I can see in here, 7/25 comes from the sine theta that we had before. So that's there. And also moments give us our last equation. So taking moments at A, we'll have, I always do it from the ground, 4 times 96 over 5G, because that distance is 4, remember, halfway along this rod, is equal to R times 5, because that's R there. It's okay. And now I think we have enough information here. We have 1, 2, 3 unknowns, and we have 3 equations. This should be good enough. I can just go ahead and work R out immediately from this. It's going to be this, in terms of G, of course. And I can shove those values into these 2 equations. First I put it into this one, which actually allows me to work out F, which is good. So again, just typing all this in, getting this. And that allows me to then find mu if I put them both into there. Both of these 2 results that I've got, so and mu gives you that. It's less than 1, so that seems good. Find the magnitude of the resultant force at A. Now, the resultant force at A is the resultant force of these 2 things. These are the 2 forces at A. So we want to find the resultant of those 2, which just means doing the 2 of them squared, square rooted, right? So mu F is this, right? Mu times F. In fact, thinking about it, you didn't actually have to work out mu, did you? Because you could have just done 7/25 times R to work out mu F. And then you have F from this bit. Yeah, okay. So, okay, we have, updating the picture, we have F is this, and we have mu F is this. So the resultant force at A is this thing squared plus this thing squared square rooted, which is what I've put all of this in, and then you just type that into a calculator and you get this. Using G as 9.8, I presume, is what I did. Okay, so then there's some more stuff. It's in equilibrium, but it's not modeled being uniform anymore. Given the center of mass is assumed to be closer to A, so the center of mass is apparently coming down here somewhere. How would this affect the normal reaction? Well, it would decrease, right? Because if you move this, if this force here, this 20G, is acting closer to here, that reduces the distance from here to here. And so this moment is decreased. It's only, say it moves down to the point 3 along. This would be a 3 now. But this moment still has to be balanced, right? Because the thing isn't turning still, it's still in equilibrium. So therefore R would decrease as well to make this still balance if this decreased here. So it would decrease, is all you have to say. Good, question number 5 then. So we've got a SUVAT question with some stuff in here. So first let's break down this 20 meters per second into 20 cos 30 this way and 20 sine 30 this way. Of course, sine 30 is a half and cos 30 is root 3 over 2, so I'll just fix those up like this. And then we can break out some SUVAT, of course. We can look at these SUVAT equations from the formula book, which I'll bring up in a second. Up, down, and left, right, we need to separate out. So up, down, we've got a SUVAT velocity of 10 initially, and left, right, 10 root 3. Acceleration up, down is minus 9.8, minus because acceleration works downwards towards the Earth. And left and right, there's no acceleration because there's no air resistance or anything like that. And t is, of course, 2, it says in the question. I think it says t is 2. So, and that applies to both things, of course. Now, we've got some missing values here. I think we can find them all. It's actually asking me for velocity of v the instant before it collides with q. It collides with q at 2 seconds. So you can just go ahead and find the v's first. I'm actually not going to because I didn't read the question. So what I first did was used from the formula book. I first found s, which is the distance this thing goes in 2 seconds. Now, I had a plan in my head, which is why I was doing this. I just wasn't reading the question. I knew what the question was asking me, but I hadn't actually read part A. I was just doing this straight away. So okay, let's just do this first anyway. I'm ignoring part A essentially, is what I'm saying there. So we don't have v, so we're going to use this formula here. We can just plug in all the values to find the s distance, or displacement I should say, and it's 0.4, which means that it must, after 2 seconds, go up and then down, and then is 0.4 above the ground after 2 seconds. So these two things meet very close to the ground. They both go up and down again and meet very close to the ground. Anyway, we can also find the left-right displacement, which is this. And so we can plug those two values in, and now I actually read the question and saw that I was actually just being asked for the velocity. So that's what I did. I used v equals u plus at in these two things separately to find a horizontal velocity of that, and a vertical velocity of that, and a horizontal velocity of that. Of course, doesn't change because there's no acceleration. And of course, it's asking me for. I was a bit confused here. Velocity. What you're supposed to do is work out the speed based on these two components, and of course, you do that by just. I don't know why that's been written twice, just ignore that. You do that by working out this squared plus this squared square rooted. So the speed is this. And then you also work out the angle that it's going to the vertical. So it's going down at 9.6 and across at 10 root 3. So tan inverse of 9.6 over 10 root 3 gives you an angle of 29 going downwards. Imagine a triangle in your head like this. That's down 9.6 across 10.3. Tan inverse of 9.6 over 10.3 is this, and you're supposed to say something like this. It's got this speed, and it's going at an angle of 29 below the horizontal, so it's kind of going down this way. Apparently that's how you're supposed to finish that, which I haven't actually seen before, but I don't teach that much mechanics, so that's probably why. Good, then part B, and I've done quite a lot of the work I already need to do for part B, because what I've said is, after 2 seconds they meet at this point, which is 20 root 3 along this way and 0.4 up this way. So what that means is, if I break out some Suvat equations for the other particle, its initial velocity obviously is u sine theta upwards and u cos theta acrosswards. These things are all the same. Now, how far does it go? Well, it also goes 0.4 upwards, and acrosswards it goes 50 minus 20 root 3. And I think I can use all of this to find u and theta, because I can just break out the equations that don't have v in them, which is the same one I used before, and just plug all those in, and the numbers get down to this, and then I can do the same thing over here, and plug all those numbers in, and I get down to this. And so this is just a simultaneous equation, right, in u and theta. So now I can say, well, there's my two equations. If I do this divided by this, the u's cancel, this becomes tan theta. This divided by this is, of course, this. Type that into a calculator with tan inverse, and you get this. And then you just plug that value into there, and you find u is this, and you'll have your answers. State one limitation, other than air resistance, the other banging one to always say is about modelling the things as particles, and that's the entire paper.